SleepStats v4 opens recorded files from Signal Solutions' Piezo Sleep system for analyzing rodent behavior. This is a major upgrade from SleepStats version 2X, with a more accessible presentation of graphic and data export options, as well as additional functionality. There are 3 versions of SleepStats v4 with increasing levels of functionality: Lite, Base, and Pro. Lite is a free version that can be downloaded from the Signal Solutions website. Base is the standard version that is included with a Piezo Sleep system order and primarily analyzes sleep and wake. Pro is a premium version that includes activity analysis and a 3-state wake, REM, and NREM classification analyses. This video will walk you through using SleepStats v4 Base and Lite. Start by clicking on the SleepStats desktop icon or through the Windows Start menu. Once launched, a recorded file can be opened. Navigate to the File section window to the folder containing the recording to open the feature vector file. Once the file has loaded, the graphic characterizations related to all recorded channels automatically appear. These can be viewed by clicking on the relevant tabs, which are the % daily sleep values and the % sleep values in light and dark. These graphics are computed the same way as they were in SleepStats 2X. The other SleepStats plots tabs are for a single channel analysis, and if we click on their tabs now, the plot area is blank. For now, let's look at the % daily sleep plot and the options for producing this graphic. This plot computes the percentage of time spent sleeping over an integer of multiple days, based on the light-dark period setting, which by default is 24 hours. Full days are counted from the first light onset to the last light onset. The time before the first light onset and after the last light onset are excluded from the computation. There should be at least one full light period followed by one full dark period for these plots. Partial days in the sleep percentage computation can bias results depending on the light-dark state of the extra time added. When the recording does not include 2 light onset times, the whole file is used in computing the daily sleep percentage. If the partial days of the experiment are important, then the % sleep/wake over sliding interval plot tab can be useful to examine sleep or wake percentage as a function of time from over the whole recording. This plot tab will be explained later in the video. Graphs can show up to 16 channels at a time. If your system has more than 16 cages, an arrow icon will appear so you can page through the graphic to see the additional channel results. % sleep in light and dark plot segments out all the light and dark intervals from the first light onset to the last, and it presents the average over all days in side-by-side bar plots. If a full light period followed by a dark period is not included in the recording, no graphic will be shown in this case. The next 2 tabs allow the user to view the numbers driving the behavior characterization. These plot the sleep-wake decision statistics, which are likelihoods resulting from a machine learning process. It also allows for various overlays of recorded data and parameter estimates and observing the data at various resolution scales. For this example, we opened a file where one of our environmental sensors was used to collect light levels, temperature, pressure, and humidity over the duration of a recording. In this case, a file with an env extension is created in the data directory. Let's select Cage 3 and look at the time series of decision statistics. The x-axis is in hours and starts with the hour of the day the recording started on a 0 to 24 hour scale. This one started at about hour 15.5, and the number increases without a reset each day. So, multiples of 24 correspond to midnight of each day. The light and dark onsets are indicated as shown with the vertical broken lines. The y-axis is the likelihood of the animal being in a sleep state, where more positive implies sleep is more likely. The green line is a decision threshold, such that times where the decision statistics are greater than the threshold are classified as sleep, and the ones below are classified as wake. This threshold is adjusted automatically by an algorithm that minimizes the variance between the two classes. This can also be changed in the text box here. The manual has more information regarding this. Decision stats are computed for every 2-second interval. We can view this better by zooming in. We can also overlay the recorded pressure signal, local breathing rates during sleep, and environmental data like light levels, temperature, pressure, and humidity if our environmental sensor was used during the recording. Let's look at using the zoom and pan features of this graphic with the various plot overlays. The zoom and pan feature icons are activated when the mouse cursor is in the plot area. When selecting the zoom in option, the cursor should appear as this crosshatch when moved onto the plot area. If it does not appear immediately, move it off and on the plot area. For some PCs, there may be a delay depending on their processing speed and memory. Now, click and drag out a region of interest like so. This is near a major sleep-wake transition. If the plot zoom or pan is turned off like this, the cursor remains an arrow and indicates the X and Y values of the line plot like this. We can overlay the signal created by animal movements, which are proportional to the pressure changes on the cage floor. At this time scale, some of the signal properties correlated with sleep and wake can be observed. Notice the higher, more irregular amplitudes are in regions classified as wake, and the lower, more regular amplitudes are in regions classified as sleep. We can also pan to another area. As we move away from the original overlay area, we see the sensor data points are missing. These can be restored by updating the sensor data like this. Now, here are areas with likelihoods close to the decision threshold. These correspond to rest, since the sensor signal values have relatively low amplitudes that are not as regular as in the case of sleep. To zoom back to full signal, we can hit the home icon. This is useful if the pan and zoom operations become unstable from doing too many zoom and pan actions too quickly for your computer to keep up with, and the queued actions put your plot in an unexpected area. We can update the pressure signal data, and we can see a low-resolution plot of the sensor data showing general areas of high and low activity over the whole recording. Let's turn off the pressure data overlay and select the estimated breath rate overlay, which shows the estimated rates in cycles per second during sleep. We can zoom into a short time scale to observe some of the breathing dynamics during sleep. Here we can see breath rate estimates ranging between 2 and 4 breaths per second. This uses the same y-axis scale as the decision statistics, since the range includes a typical respiration rate in cycles per second. Now, let's add the sensor signal. This time scale is too big to observe the cycle variations from breathing. However, the breath rate estimates effectively quantify these over 2-second intervals. We can also see some artifacts at a transition between wake and sleep where a short activity burst included in the estimate window interferes with the estimation, generating a suddenly low value. Breath estimation accuracy requires a good signal-to-noise power ratio. So, if this feature is used, it is important that the respiration signal is consistently stronger than noise signals from the room. Now, let's overlay the information collected from one of our environmental sensors. If the environment sensor data file is in the folder with the feature vector file, this options box becomes visible. If multiple sensors were used, they can be selected here. In this case, only one sensor was used in the room where the data was collected. Let's overlay the light level data. The value ranges are quite different from the decision statistics, so a second y-axis on the right is used in lux units. This right y-axis will be used for all the environmental parameters. As you can see, The lights went on close to the scheduled onset times provided during the recording session setup shown here. Let's zoom in on one of the transition points. We can see there is a slight delay from when the lights actually went on, as well as a warm-up period for the lights to reach a steady state value. We can also see temperature changes varying between 74 and 73 degrees, relative humidity varying between 20 and 60%, and barometric pressure close to 29 millimeters of mercury with a slight dip after the second light onset. The environment data can also be exported to CSV files for both the base and light versions. The sleep-wake decision histogram is useful for assessing how well the classifier distinguishes between distinct sleep and wake behaviors. For an animal with typical sleep and wake behavior patterns, decision statistics over the course of 24 hours should cluster toward negative values for wake and positive values for sleep. A bimodal histogram of the decision statistics usually indicates that the algorithm worked as expected, and this allows for a relatively accurate auto-threshold setting to separate sleep and wake behavioral intervals. The adaptive threshold is also shown located near the saddle point. For a typical recording greater than 24 hours, clustering to either side of 0 suggests reliable results. However, for more varied behavior during the wake activity, the histogram may not show a sharp peak for wake or a broader peak depending on the variety of activity. In some cases, there may even be multiple modes either due to external room/cage vibrations or animal behavior. This can sometimes cause the automatic threshold to be set less than optimal. In this case, it would be a good idea to check the sleep-wake decision statistic time series plots to make sure the sleep-like and wake-like waveforms are being separated properly. More on the meaning of this histogram and threshold adjustment is presented in the manual. The percent sleep/wake over sliding interval plots the percent sleep or wake over a sequence of time intervals that are incrementally advanced over the entire data segment. This graphic is good for looking at the response to each of the light and dark onsets. The time index denotes the midpoint of the sliding interval. The increment between intervals and the interval duration can be changed in the text boxes below, which are in units of hours, like the x-axis. Or, you can switch the graph between sleep or wake percentages. Here we can see a difference in the data when changing the sliding interval length. A longer interval creates a more smooth graph showing longer-term trends, while a shorter interval shows more local changes in behavior. The sleep/wake bout length histogram plot computes histograms of sleep and wake bout lengths. This option is not included in SleepStats for Lite. Several options for computing and presenting bout lengths can be selected in the panels shown here. This option determines how the histogram is computed relative to the light and dark phases of the recording. This option bends the bout lengths over all 24-hour segments from the first light onset to the last light onset, while this option bends the bout lengths separately in the light and dark phases. If two light onsets are not included in the recording, then the whole recording is used. The bout lengths are bent over logarithmically scaled ranges. The next box selects the normalization of the histogram bends. The percent state time adds all detected bout lengths in each bend interval and divides it by the total time the animal spends in the target behavior. So, each bend represents the percent time the animal spent in that bout range for the selected state. The number of bouts just counts the number of detected bout lengths in each bend interval. There are two ways SleepStats computes a bout length, which can be selected from the lower panel as either roundup or consecutive intervals. For both methods, consecutive sleep detections within the minimum bout length interval is incremented through the series of detected states counting the length of the bout. If the interval contains more than 50% of the target behavior, the interval is labeled with that behavior. For the roundup method, the whole interval associated with each detected time sample is expanded, So all points in the minimum bout interval are labeled with the target behavior, and the bout length is from the beginning of the first interval to the end of the last interval in the bout counting methods. That is why there are no bouts less than the selected minimum bout length. This was the method used in SleepStats 2. For the consecutive intervals method, consecutive labels for the interval centers are counted without rounding up to the full minimum bout length for the beginning and ending bout. So this simply counts the consecutive minimum bout length interval with greater than 50% of the target behavior. For example, if an isolated minimum bout length interval passed the greater than 50% rule and the interval before it and after it did not, it would just be a bout length of 2 seconds. The consecutive interval method results in shorter bout lengths. While the graphic displays are good for efficient exploration of the data in sleep-wake behaviors, it may not be appropriate for some experiments. In this case, the user can export information to CSV files for custom analysis. This program has several options for exporting data and parameters to comma-separated variable files, which can be opened by other programs for further processing and analysis. This drop-down menu presents a list of options for exporting the data to a CSV file. The Lite version only offers a few export options. The %sleep-wake per user-defined interval option generates a CSV file with %sleep computed over a user-defined interval in minutes with a default value of 60. The first column of the export consists of the timestamps corresponding to a sequence of start times for each interval. Once the export button is pressed, an options menu window will appear with the start and stop times of the complete file and the last saved interval. These text boxes can be edited to change the time window for the export, the interval for the %sleep or wake calculation, and the base file name for the output file. In the CSV file, the timestamps begin with the start time from the pop-up menu, which represent the actual date in a 24-hour format. If time is selected outside the recording range, it will be coerced to the beginning or end of the file. The segmented bout stats option exports several statistic files that describe sleep or wake behaviors. This includes the histogram bin values over the selected start and end time of the export. And over a sequence of user-defined time intervals, it can export the mean, median, standard deviation, 10th percentile, 90th percentile, qth percentile, and the percentage of bout lengths greater than a user-defined threshold bout length in seconds. Since not all of these statistics may be relevant to a study, an options panel shows under the Export drop-down menu, which allows the user to select the statistic files to export, as well as whether the bout statistics should be calculated for sleep or wake. For each item selected, a spreadsheet is generated with the corresponding statistics for each time interval and channel. The histogram output, however, exports the histogram bin values for the entire range selected. The interval in minutes is ignored. After clicking on the Export button, a window will pop up, allowing the user to change the time range, the base file name of the CSV output, and the size of the intervals for the stats to be calculated on. The generated CSV files are distinguished by strings appended to the base CSV file name. The other exports work in a similar manner and are described in the manual. This concludes our video covering the basic operation of the latest version of our analysis program SleepStats. Thanks for watching this video.